Well, thank you for that introduction. I'm actually gonna give you a mostly data-free talk. so, we'll see how you guys like this. But I really want to thank Terry Jo earlier today. She's someone that I've known for a little bit because we work quite a bit also with a number of the foundations in Combined Brain, and this is an idea I've been kicking around with Terry Jo a little bit, and you heard HUD kind of allude to some of these ideas. So I promise we didn't collaborate on this. I think we're just kind of all thinking the same thing right now in today's world. So my title changed a little bit from what's in the schedule, but I think you'll see why. So I wanted to start with this picture, which is a picture of our community. I guess this is actually not from last year, but from two cycles ago. But what I really like about this picture is that it really emphasizes this community, right? The largeness of this community and how CDG Care is bringing together groups of people that otherwise would be on their own journeys. And this is, in fact, what most of the foundations I work with are. They're on their own journeys, but we have so many disorders all together and kind of working together. And I really like that. And I think that that's a really great way to kind of couch what I'm going to talk about. So like all rare diseases, they're rare, given the name. And most CDGs are ultra rare, affecting fewer than 100 people worldwide. And I realized my number is off a little bit, but there are nearly 200 CDGs that have been identified, but in my lab, our count is there are at least 250, 260, 70 glycosylation genes, so there's more. There's more room in this community. And the collective impact is that while each of your disorder is rare, the global community is quite common. And we can see that because CDG Care brings us together to kind of try to pull this off as a group rather than alone. But I think for parents in the room, it's quite obvious we can't solve CDGs one at a time. It's a big ask, and it's a big struggle when there's over nearly 200 and counting. And so in a world of limited resources, we can't do this alone, right? Each parent can't fight for their own CDG alone, and each foundation can't do it alone for their own disorder. We really have to think about how we can do this together. So it makes, I've been asking questions like, what do we have in common as different CDGs? What is the shared clinical story between all of your children and all of the different CDGs that are represented in CDG Care? And what's the shared biology? As parents, you start talking with each other in this room, you meet other parents who are struggling with different forms of CDGs, but you realize that your kids are all struggling with the same kind of organ system issues, right? Nearly every kid has neurological problems, developmental delay, seizures, and so on and so forth. And so that's already a common point that brings us all together. But as parents know, the therapeutic odyssey is lonely. We used to talk a lot about the diagnostic odyssey being lonely, and certainly it's still a challenge, but it's certainly much less of a challenge now. And now many families are thinking about, well, what about the next odyssey, that therapeutic odyssey, trying to find some help for my kids. And it feels lonely because we feel like we have to do it ourselves, right? We have to try to fundraise for our own family, for our own kids, for our own disorder, and it's just not sustainable that way, right? But science is actually exactly the same way. It suffers from exactly the same problem. We think that we can only study one disorder at a time, or we can only find funding to study one disorder at a time, or we feel like as scientists we have to understand every A to Z point about the biology before we can even think about therapies. All that makes it lonely, it makes it long, and it makes it hard. My lab is no different. We're guilty of that. We've spent the last 10 years thinking about how individual patients are different from each other, how we're cutting the group even smaller. And certainly that's important. That's important for personalized medicine and thinking about inter-individual differences, but it makes it harder to think about the commonalities. It kind of pulls us away from that part of biology. And we're also looking for drugs, right? We're looking for drugs for different CDGs, different rare diseases, one at a time. And again, that's a great strategy, but it's also slow and sometimes can also be lonely in science. So, just like there are common human experiences, there are also common scientific themes. And I want to kind of pull on that string a little bit for CDGs, and I think you'll kind of see what I'm talking about. So we just step back to the basic biology. This is almost the most science you're going to get in this talk. You step back to the basic biology, you'll see that end-linked glycosylation is on top, GPI anchor biosynthesis is on the bottom. I only picked these because these are the easiest figures I had at hand. But you'll notice that both these pathways happen in the part of the cell called the endoplasmic reticulum. Some of it happens on the outside, some of it happens on the inside. They use the same molecules, same sugars to build these chains, and then they send proteins somewhere else. There's lots of commonalities there, even in kind of that very general summary I just gave you. And that already kind of suggests that there must be common biology and common things that we can pull on to try to treat these disorders. But I wanted to actually get a little bit more specific and highlight some of the things we've seen over the past 10 years or so in my lab, and why I think that this is really makes me enthusiastic for trying to find common therapies. So one of the pathways we've kind of been falling into over and over again is the dopamine pathway. It's kind of this reward pathway in your brain, right? It's also affected in Parkinson's, but it's also important for many disorders like CDGs. And so I wanted to tell you about how we're finding commonalities in the dopamine pathway for DPHD1, CDG, PIGA, and NGLY1. And these are just happens to be the ones we're studying in the lab. And so it's certainly not limited to this. This is the second most biology you're going to get in this talk. But you don't have to know anything on this slide. You know nothing. There's lots of colors on it. The colors tell you that there are differences. But I want you to just kind of keep in mind that on the left is the PIGA, on the right is DPHD1. Oh, that's not good. Here on top is where dopamine is made in the presynaptic neuron. Dopamine is dumped into the synapse, and then it signals in the postsynaptic neuron. That's all you need to know. And there are differences on here for sure, but I'm gonna kind of blank out the differences and draw your attention to the similarities. So this is the signaling part of the pathway, and for both PIGA and DPHD1, we've done screens for them and found drugs that inhibit the dopamine 2 receptor that both improve the models. And then we can do the same thing genetically by genetically removing the dopamine 2R receptor, and that improves the model, kind of validating that drug response. We can use drugs or genetics to get rid of dopamine 1 receptor signaling, and that makes both models worse. And we can use drugs and genetics to improve dopamine transporter activity, and to remove dopamine transporter activity, and that makes things better. So this is, with almost no details, you can see how there's so much opportunity here for common therapeutic thinking and common therapeutic approaches for these seemingly very disparate disorders. PIGA is GPI anchored, DPHD1 is end-linked glycosylation. And I'm not going to show you here, but we're also finding similar things for NGLY1 deficiency, which is even more different than either of these disorders. That the dopamine pathway seems to be a pretty important therapeutic target for these CDGs. And kind of the second pathway I wanted to highlight was this pathway called GSK3 beta signaling. And I'm going to highlight commonalities between PIGA and NGLY1. And this diagram is small, so you don't have to read it. And also, for the scientists in the room, I don't wish studying GSK3 beta on anyone. It's the most complicated thing in the world. And one reason that makes it so complicated is the fact that it's basically a master switch for almost everything in the cell. It turns many things on, and it turns many things off in the normal of its kind of normal function. But because of that, it's been studied in many different disorders, in cancer and neurological disorders, and many molecules have been developed to enhance or remove its function. And what we found is that when you remove the function, or when you decrease the function of GSK3 beta, some pretty interesting things happen in CDGs. For example, in our PIGA models, they have seizures just like the kids. And when we reduce GSK3 beta in the PIGA models, it reduces their seizures quite a bit. It's genetically and pharmacologically. And what we see with NGLY1 is that when we reduce GSK3 beta signaling in those models, it improves their survival. They live, they don't die anymore. And so here is another example where we see convergence of the same pathway in two very different disorders, improving the outcomes of these CDGs. And so dopamine pathway, GSK3 beta signaling are just two examples of how we're seeing things kind of converge. And it makes me think, if there's all this common biology, we have to be able to find common medicines as well. And so, as many of you know, because introduction, that we've spent the last 5 years doing drug repurposing, trying to find FDA-approved drugs that may be able to be reapplied for different CDGs. We've worked with many of you, and we have different molecules in different levels of testing, and we've done this for about two dozen rare diseases, and about half of them have been CDGs. So we have quite a bit of data as well. And we do all this in the fruit fly. I always like to plug that, make sure people know that it's a good model. And so we have 10 CDGs that we've done drug screens for, and we've thrown the book of FDA drugs at them. What can we learn from them? And if you look at all the 10 screens, it might not be surprising to you that maybe there aren't actually any drugs in common between 10 very different CDGs. That's maybe not too surprising, or maybe we were being a little too enthusiastic. But when you look at how many drugs overlap 9 out of the 10 screens, there's a single drug that overlaps 9 out of the 10 screens. And maybe 9 out of 10 is also a little too enthusiastic, right? You don't expect one silver bullet. So if we drop it down to 8 out of 10 screens, we have 12 drugs that can rescue the models to some extent in any 8 of the 10 screens we've done. If you drop it just a little bit more, 7 out of 10, 70%, still pretty good, we have 50 hits that can improve the models in any 7 of the 10 CDGs we screen. So that's a lot, right? And that's a lot to think about. But that tells us that even with only having done 10, there are ways that we can think about drugging these rare diseases in common ways, in common approaches and common pathways. And this isn't just an academic exercise for the lab. It's actually really important for thinking about clinical trials. And so what we're starting to think about is how do we screen for groups of disorders at a time, using representative diseases, find a common set of drugs that we can then go and test those 10, 15 drugs in all the CDG models. And maybe we'll find a drug that hits all of them. That would be great. But we're more likely to find drugs that fall into one subset of CDGs or another, and so on and so forth, as you can see on the left over there, on the right. And again, this isn't just an academic exercise. It isn't just a lab experiment. We want to think about how we can be very purposeful about how we screen these disorders from the beginning, so that we can think about basketing these disorders into groups. And basketing diseases into group is, again, something that we can do in the lab, but it's really important for clinical trials. We can think about ways in which we can increase the numbers of patients we can put in a clinical trial, because maybe 2 disorders have a particular drug in common, then that increases the numbers and also makes it easier to kind of meet some of the standards that the FDA has. And so maybe we find a drug A that fits all the CDGs with this giant basket, right? And that'd be great. But we can also find drugs that fit maybe 10 disorders for drug C, or maybe 5 disorders for drug B, or maybe even just 2 disorders for drug D. And any of those outcomes is better than doing it alone, right? And having multiple disorders grouped together, I think, can push clinical trials forward faster, and makes that journey a little less lonely. So we can't solve CDGs one at a time, and this is kind of how I've been thinking about how we can move forward. We can't do it one-on-one forever. This is just not, we're like the only ones doing it in flies, right? And so it just can't go on like this forever, and we need to think about ways to move forward. And of course, groups like CDG Care have really kind of helped pull us together, and we should take advantage of this community to also use that community spirit to try to find drugs together. All right, so that's my talk. We have a couple posters. Mimi is a grad student who's working on the PEG-A dopamine story. She has a poster on that. Kate Beebe runs our drug screens. She has a poster on kind of how we do those drug screens. And Jean Marie is a new postdoc in the lab starting a PMM2 project. And I should say that I just told you how we shouldn't be doing single drug screens, but we're still doing them. And so if you want to work with us, I'm happy to chat with you about it. We've done about 10. We have a couple other CDGs spun up and ready to go soon. So we're chugging forward, but we're looking to the future as well. Thank you.